Okay. Yesterday we have seen so always shortest path with a general weights problem. What are the different I mean advantages of this Bellman code algorithm? Similarly, what is the disadvantage of Bellman code algorithm as seen? Okay, yesterday we have seen something like this. If negative edges, this cycle value will be equal to negative, then Bellman code algorithm cannot be cannot be gives you perfect answer. So thereby, it could not be considered in terms of doing some kind of operation in uh, Bellman code algorithm for doing the same. Now, now, what is Bellman code algorithm and how it could be gets executed? So let us see. So let me execute the Bellman code algorithm first. Then we'll go ahead with the algorithm here, final algorithm here. So what exactly we're trying to perform here is if you have so increasing lengths of k edges are there with you, then you are expected to find the shortest paths at most for k number of edges, where k will be the so k will be connected with the several number of vertices here. Or otherwise, in other words, find the shortest path can have at most n minus 1 edges. Instead of k, you could write n, where n will be the number of vertices here. Okay, number of vertices here. So n will be equal to some 5. So 4 times you have to identify. So 4 iterations could be taken so to find the shortest paths from starting vertex to all other vertices. But these vertices are directed vertices. It is a digraph, and the directed vertices will be so taken into consideration. Then followed by, so if you have more than n edges in the problem, or identification of more than n edges in the problem, then obviously it has been framed on particular cycle. Okay, so forming of cycle is not that much important, but forming of cycle and the weight of that particular cycle should not be negative. If it is negative, so obviously so the problem will be never terminates. The problem would never terminate, so that you could not get a proper output from the Bellman Ford algorithm. This is the basic pitfall of Bellman Ford algorithm. So this is the basic problem. Then to do the entire operation, we'd like to perform. So we'd like to take into consideration of the thing here. The length k will be the length, or first iteration kind of length. K will be taken as first iteration kind of length. Right away from a vertex V to U, will be breaking up something like this. We need to identify a path. We need to identify a path that k minus 1 will be taken into consideration, so that v to another neighbor of u, that is w. Okay, it is some neighbor of w of u. Okay, so let us take the formula here. Then so here you could understand very easily. Relaxing all vertices, relaxing in the sense reducing the distance, reducing the cost from all vertices for n minus 1 number of times, whereas n will be the number of vertices here. How you can relax? What is the relaxing function which was introduced here? If a distance of u plus cost of u comma v, there are two vertices u comma v. Distance of u plus cost of u comma v is less than distance of v, then distance of v, then we need to update in such a way. Distance of v will be equal to distance of u plus cost of u comma v. If this is less than, if this particular equality will be gets true, then we have to make such kind of modification. If it is not true, then obviously available distance will be smaller than the addition of u comma, distance of u plus cost of u comma v. Okay, so this is the basic formula which we have to follow to attain So all pair shortest path problem with general weights. So remember, it is always accepting negative edge weights. Negative edge weights are accepted. Number one. Number two. So cycle length or cycle weight must not be equal to negative. Okay, these two are keep in our mind. Then you have to run this particular problem. Okay. So let us take this particular problem here. So I have given this relaxation kind of formula. So here for our reference. So let us consider this is the graph which we have taken into consideration, and we need to identify shortest path from a source vertex, single source, that is A to all other vertices. So that is the basic idea where exactly we have to consider. I'd like to perform everything on this particular graph itself. On this graph itself. So in the first step, what we are supposed to do here is we need to draw or we need to write all vertices at once. All vertices at once. All edges at once. And initially, so cost, distance of, not cost vector, distance of A to A will be equal to 0. A to A will be equal to 0. And the distance right away from A to B, initially, we don't know what is the distance here, so that it is not known to you, so that we have to consider it as infinity here. And it is also considered as infinity. It is also considered that as infinity. Here also consider that as infinity here, because we don't know what is the distance. So right away from A to B, A to C, A to D, A to E, and A to F in the initial stage. Okay, this is the starting time of the particular problem. Then how many times you are supposed to relax these edges? N minus 1 times. N minus 1 times. How many vertices are here? So A, B, C, D, E, F. Totally 4 plus 2, 6 vertices are there. So you are trying to apply this relaxation for 5 times. So which will be gives you 6 minus 1 will be equal to 5 times. Okay. So therefore, we are doing this particular operation manually so that it could becomes to us up to 2 to 3 times. After third time, so you may observe that there is no change in the cost of in the distance of so every vertex from A. So therefore, first we have to consider first edge, that is A to B. Okay, let us consider this particular vertex will be so u, and this is v, for example. Okay, this is u and this is v. So try to observe this particular formula. Distance of u, what is the distance of u? That is 0. That is 0 plus cost of u comma v. What is the cost of u comma v? That is 6. So 0 plus 6 is less than distance of v. What is the distance of v here? Infinity. Yes, infinity. This is true. Because it is true, we have to modify distance of v equal to distance of u plus cost of u comma v. Distance of v is infinity. Actually, we have to rewrite with as 6 here. So first edge is gets over. Second edge. Let us take into consideration of second edge. A comma C. So between A and C, the distance of A equal to 0, and the cost of A to C is 4. 0 plus 4 is less than infinity. Yes, it is true. So therefore, you have to modify it. Modify it, which is 4 here. Which is 4. After that, the next one is A to D. The distance of A equal to 0. Cost of so A to B is 5. 0 plus 5 is less than infinity. Yes, it is true. Therefore, you have to modify it. You have to again modify it. Then BE. Then BE. So distance of B is 6, and the cost of B comma E is minus 1. 6 minus 1, that is 5. 5 is less than infinity. Yes, it is true. So therefore, the distance will be so 5 here. Obviously, next one is CE. Next one is CE. So this is the so edge we have. The distance of C is 4, and the cost of C to E is 3. 4 plus 3 is 7, but actually here it is already 5. So 7 is less than 5 is false. So therefore, no change here. There is no change here. And then the distance of DC. Distance of DC. So DC in the sense of this particular thing. Distance of D is 5, and cost of so DC is -2. 5 minus 2 will be so 3, which is less than 4. Distance of vertex B, that is 4. So my 3 is less than 4, so that we have to readjust this one more time. That is 3. 5 minus 2 equal to 3. And the next D comma F. So D comma F will be distance of D is 5, and the cost of D to F is -1. That is 5 minus 1. That is 4. 4 is less than infinity. Yes, it is true. So therefore we have to modify it as 4. Then distance of E to F. Distance of E to F. So in this way, E to F is this way. So distance of E is 5, and the cost of E to F is 3. 5 plus 3 is 8. 8 is less than 4, which is false. Therefore, no updation. Distance of C to B. Distance of C to B will be seems like this. So distance of C is 3. So cost of C to B is -2. 3 minus 2 equal to 1. Yes, 1 is less than 6. It is true. So therefore, update one more time. Update one more time. So after first iteration, we did everything for first time. That is the first iteration. So has been completed here. Number 1 iteration has been completed. All edges have been relaxed. It has been completed. Then go for second iteration. Second iteration, whether it is fulfilled or not, let us check one more time. Let me take another color, then it could be very easy to identify what is the second iteration here. So let us go ahead with all edges one more time. So apply this particular same formula for number of times on each and every edge, so that so A to B, the distance of A equal to 0. So let me eliminate this U and V, so that you could not confuse. Okay. However, distance of A is 0 plus the cost of U comma V, that is 6, which is less than 1, which is false. Therefore, 1 will be as it is. Then, so A to C is in the sense this one. So distance of A equal to 0 plus cost of A to C is 4. So 0 plus 4 equal to 4. 4 is less than 3, which is false. Already it is 3. So keep as it is. So A to D. Next edge is A to D. Distance of A equal to 0. Cost of so A to D equal to 5. So already it is 5. There is no change at all. Then B to E. So B to E in the sense this one. Distance of B is 1, and the cost of B to E is -1. 1 minus 1 is equal to 0. 0 is less than 5. Yes, you can modify this. You can modify this. 1 minus 1, that is 0. 1 minus 1, that is 0. So at BE, so some modification was happened. And then consider CE. So C in the sense, this is the thing here. So distance of C is 3, and the cost of C to E is 3. 3 plus 3 equal to 6. 6 is less than 0, which is false. So there is no change. DC right now. DC is 5 minus 1. Distance of D is 5. Minus 1 is the cost. 5 minus 1, 4. Already it is 4. So no need to change. Then followed by DE and DF. DF in the sense, so this one here, where DC, DC in the sense this one, here also there is no change at all. 5 minus 2, that is 3, already it is 3, there is no change. So DF also, there is no change. EF, distance of E equal to 0, and the cost of so E to F is 3. 0 plus 3 is 3. 3 is less than 4. Yes, it is true. So therefore, one more modification here, that is 3 here. That is 3 here. CB is the same. So distance of this one is distance of C is 3, and the cost of C to B is -2. 3 minus 2 is 1. 1 is less than 1. So it is not true, it is as it is. So second iteration also completed. Iteration number 2 also completed. Now let us go ahead with the next iteration. So third iteration, iteration number 3. So iteration number 3 will be taken. Again, we have to take all these edges and we can perform this one here. So distance of A to B, distance of A to B, 0 plus 6 is less than 1 false. So 1 is as it is, no change at all. A to C, so 0 plus 4, which is less than 3 false. So it is also as it is. A to D, so 5, 0 plus 5, that is 5, 5 less than 5, which is also as it is here. B to E, B to E in the sense 1 minus 1, that is 0, 0 less than 0, so as it is, there is no change at all. So C to E, C to E. So C to E in the sense, 3 minus 3, 3 plus 3, 6, 6 is less than 0, no change at all. Then D to C, D to C also, so 5 minus 2, that is 3, so 3 is less than 3, so there is no change at all. Then D to F, and everything is not at all changed. There is no change. After completion of the third iteration, we could not find even one distance is not changed. Therefore, distances will be, so A to A will be equal to 0, and then A to B will be equal to, so 1, A to C will be equal to 3, so then A to D will be equal to 5, A to D will be equal to 5, so A to E will be equal to 0, A to E will be equal to 0, A to F will be equal to, so 3. This is the final answer. So systematically, when we have to run the same problem by using any using that particular algorithm, so using that particular algorithm, so it could be run for 5 times. It could be run. So this must be followed. 5 times could be followed. So after third time, there is no change at all. So we are checking this one. So it could be gets exited out by manually. If it is actually implemented by using algorithm, it must be run for 5 times. It must be run for 5 times. Okay, these are the distances. This is the outcome of your algorithm. Then what is the algorithm here? Algorithm is this one here. All pain shortest path. First of all, we'd like to note down the cost. We'd like to note down the all cost. Then followed by, so k equal to 1 to n, and we need to say minimum of whatever the operation we have did here, minimum of this one is being identified. Same formula has been used. Same formula will be used here, which is minimum. So therefore, we have to maintain that particular minimum. So as we see, so look at this. So as far as this particular list of algorithms, list of for loop nesting level 1, nesting level 2. So totally 3 level nesting for loops has been used. The algorithms, the complexity will be order of n cube. Order of n cube. Okay. Number of vertices will be V. Number of edges will be, so capital E. Number of edges will be capital E. Actually, so the problem will be taken, so number of edges into, so number of vertices minus 1. It is the actual thing. So for incomplete graph in the sense, what do you mean that there is no one more edge? Actually, we need to draw one more edge from C to F also. There is no edge, so that it is incomplete graph. For incomplete graphs, the complexity will be seems like this. If number of edges will be equal to n and number of vertices also equal to n, it will be gives you n square. If incomplete number of edges with the graph. Complete in the sense, look at this, how many number of, so complete graph, how many edges will be there? So if number of edges will be n into n minus 1 divided by 2. These are the number of edges which will be incident from one vertex to another vertex in complete graph. Okay, into how many number of iterations which has been taken? V minus 1, where V equal to n. So therefore n minus 1 So iterations will be taken. So therefore, if you solve this particular equality, then you could get n cube. ఎలా వచ్చిందో చెప్పాలి అంటే చెప్తాను, అది కూడా చెప్తాను. సో n square minus n, so into n minus 1 divided by 2, which could be, so n square n cube n into n square into n cube, so minus n square, so minus n square again minus n divided by 2. Okay, that will be equal to, so n cube minus 2n square minus n divided by 2. So higher order will be n cube here, higher order will be n cube here, so that it will be leads this particular complexity. So therefore, big O of n cube is the, so complexity of this all pair shortest path algorithm using Bellman-Ford algorithm, which is following the dynamic programming method. This is the Bellman-Ford algorithm. Okay. This is the Bellman-Ford algorithm. So that's all. And let us open your CSC, and where is the syllabus? Yeah, here it is. The syllabus here. Yeah, we have been completed. This one also. So unit number 4 is absolutely completed. No topic is left over. Okay, no topic is left over here. Then tomorrow we'd like to start a very important thing, that is backtracking. One of the important operations, daily life, we have been operating this backtracking for a while. If the power will be lost in our house, wanted to search for a battery or a thing or any item, so you are always trying to perform the backtracking operation on it. Okay, so let us so discuss this one.